All right, in this section, we're going to investigate what we call average rate of change, which you guys have dealt with ever since probably like the 7th grade, maybe even 6th grade, for a specific type of function that we've worked with. But this, we're going to then, from what we already know, try to kind of build a bridge to other functions. So average rate of change is what we refer to as the change in output, okay, which is your dependent variable, divided by the change in input, which is your independent variable. That's one way that we can determine what the average rate of change is. If we look at this here, okay, we call that, hopefully you've seen this before in science, that triangle right there is the Greek letter delta, but delta y over delta x, and delta in mathematics or science just refers to that phrase right there, change in. So you think about functions, your output, well, that's your y, your input, that's your x, that's your independent and dependent variables. So delta y is a shorthand way of saying change in output. Okay, delta x is a shorthand way of saying change in input. Now, how do I get change in y? Thinking about if I'm on a graph, I'm in a function, change in y. Change means difference in mathematics. Okay, and the way we do difference is subtraction. Okay, so that's where we're seeing, okay, I have a difference in y, that means I must have two y values that I can subtract. Okay, now the order doesn't really matter here as long as I keep the order consistent here, but usually y2, we infer that that's above y1, so in order to do subtraction, so my quantity is positive, my distance is positive, we go y2 minus y1. And then my delta x, or change in x, is x2 minus x1. Now that formula, I hope you remember as slope. Okay, now that's if my function is a line. Okay, now we kind of clean that up a little bit and make it more suitable for all types of functions. Instead of saying y2 minus y1, we know if it's a function, instead of using y, we know because by definition that's function notation right there. And the reason we prefer to use that symbolism instead of this one is because there's more information in that. When the author writes f of x, automatically tells the audience, oh, well, what we're working with, it's a relation, but it's a special type of relation. It passes the vertical line test. Where if I just say y equals whatever, okay, I don't know that it's a function or not. So, for example, if I say like y equals, I don't know, maybe something you guys have not seen before, aren't all that familiar with. So let me write y equals, let's go, 2 sine of x minus pi over 2. I'm hoping, I'm assuming, and let's add 5 to that. I'm assuming that we don't know what that looks like. Okay, so you don't know any characteristics about that function. But if I, or this, let me say this relationship. But if I do this, you still probably don't know what it looks like. But you know one thing. You know that it now, because I've told you it's a function, it passes the vertical line test. You know for every x value, there's one and only one y value. That's the definition of a function. And now you have a little bit of extra information. Okay? So we're kind of doing the same thing here, looking at the same thing here. Okay, we've got a little bit more information when I write as f of x sub 2 minus f of x sub 1 over x2 minus x1. Okay, but average rate of change, okay, if we're dealing with a line, here it says if f of x equals ax plus b, so you were dealing with a line, average rate of change, we've usually referred to it as slope. Okay, but if you go back to your Algebra 1 text or maybe your 8th grade text, the first time that they introduced that, the section before, they called it that. Okay, so the average rate of change for a linear function is constant or the same between any two points. We've seen that. If I look at this line right here, choose any 2 points on that line, whether I choose these 2 red ones here or maybe I choose that blue one and that blue one. the average rate of change, okay, which is the rise over the run essentially, okay, is always going to be constant. It's going to be the same exact thing. That's one of the fundamental things we've talked about in Algebra 1. So it says the average rate of change for linear functions is constant or the same between any 2 points. Therefore, we usually just call it the rate of change. Okay. It says for linear functions instead of average rate of change. Something like I said, we also call it slope. It says, however, the approach is the same regardless of the type of function. Okay, so just running through an example here with a linear function. It says a dam is built on a river to create a reservoir. It says the water level f of t in the reservoir at time t is given by this function. Okay, so here's what I want to look at this, just investigate initially. At time 0, at the initial time, okay, the dam has a height or the water level is at a height of 28 and t is 0. So that's nice. Okay, so that point right there is 0, 28. Okay. And we can go through and we can see, okay, well, if I've got, 2 there, here's 3, here's 4, here's 5, and we can kind of recognize what then these other points are, other key points are. But it says sketch graph of f. I've done that, did that for us. It says what is the slope of the graph? Okay. Well, we know, because we know what the function is, we know that the slope is that right there. Okay. But we can ask the question, what is the average rate of change, or what is the rate of change, by saying, okay, well, because it's a rate, remember what rate is. Rate is, if we have distance equals rate times time, isn't rate equal to distance divided by time? Okay, so let's think about this. Distance divided by time. Well, distance, in terms of this question, would be the height of the water level. Okay, so if I say my water level right here is at 28, okay, I'm going to come over here to 5, and I look at 5, and that looks like it's at, so this is 10, what would this be, 20, 30, 40, 50, okay, so at 5, time of 5 days, then, or sorry, 5 years, we're at a height of 50. Okay, so if I ask you, what is the rate of change? Well, distance would be that there. Okay, so it's at 22. Okay, and then the time would be 5. Okay, and then I would have 22 over 5, which is going to be, now I'm off a little bit, that would be, what, 4.4 and 2, it'd be 4 and 2/5, which would be 4.4. So when I graph that point right there, I was making the assumption, I guess if we zoom in on that point, we're not, you kind of see that we're not really crossing at those grid lines. It's a little bit above it, so this number here is off a little bit, but we're seeing there that relationship, because I chose this point here and that point there, I get an average rate of change, which rate is a distance divided by a time. So that distance divided by that time gave me I'm going to say 4.5, because if I underestimated that point there. But we also know that to be the case there when I look at the structure of a linear function and what we've known since, like I said, 7th, 8th grade. Okay, so at what rate is the water level in the reservoir changing? Well, it's changing at a rate of 4.5 feet per year. And that's exactly what I've done here. Okay, this distance was feet. Okay, and this time was in years, feet per year. Okay, so that's average rate of change. It's taking that distance. Think about like an average. It's the total okay, total amount divided by how many you have, okay? So from this point to that point, the total increase in vertical distance is that amount divided by how many intervals we have, will give me that rate of change. Here's another scenario, okay? So we see this a lot. It says gasoline costs have experienced some wild fluctuations over the last several decades. Lists the average cost, or the table lists the average cost in dollars of a gallon of gas from 2005 to 2012. So the cost of gasoline can be considered as a function of year. So if I tell you it's a function of year, because if I tell you what year it is, you should be able to tell me the output. Okay, if I say, 2005, you should be able to say 2.31. Okay, 2006, 2.62. Okay, I'll never be able to say, because that's the average price of gas for that year. You're not going to have two average prices for the same year, so there's no way that this would ever violate the vertical line test. So it says find the average rate of change between 2005 and 2009. Well, quickest way, easiest way I think to do this is, okay, so 2005 is my input, and my output then is 2.31. Okay, 2009 is another input, and then 2.41 is my output. So if I want the average rate of change, remember it's change in y over change in x. Now, I just want to pay attention. I'm going from 05 to 09, and I'm seeing that from 05 to 09, we had an increase. Okay, so I'm going to go 2.41 minus 2.31, and then I'll divide that by 2009 minus 2005. So it gives me, what, 0.1 over 4. Okay. Which that turns out to be 0.025 as a decimal. Okay. So in this case, where we're in dollars, so that would be $0.025. Okay. Now, if I think about this, it's called the average rate of change. It doesn't tell me, so if I think about this, it doesn't tell me that from that year to that year, that if I apply that change, that I'm going to get that amount. Okay? So I'm not going to go from 2.31, add 0.025 to it, and get the next year, because it's the average rate of change. But what it does tell me, say, okay, add 0.025 there, add 0.025, so start at 2.31, add 0.025 to it, then add 0.025 to it, then add 0.025 to it, and then add 0.025 to it. And if you do that, how much did I add to 2.31? I did 4 iterations of 0.025, so that sums to 0.1. So 2.31 plus 0.1 gets me to 2.41. Okay, so it tells me that though there were fluctuations in between, okay, the average rate of increase was just 0.025. Okay, it's this idea. Like if I've got a graph, it might look something like this here, and I go from, let's say, that point there to that point there. Okay, and I want to know the average rate of change, which would be essentially the slope of that dotted line right there. Okay, that slope is going to be a value that is lesser than like the increase that like got me to there. Okay, so I'm going to experience, as I move along this, larger values than what that slope is. So I saw in this case a larger discrepancy between those, 31 cents between those two consecutive years, but over the average of 4 years, it works out to be 0.025. Okay, that's kind of what this series of questions is getting at here. If I look at from 2009 to 2012, 2009 to 2012, we're seeing now, okay, it was an increase. So again, I'm going to go 3.68 minus 2.41, and I'm going to divide that then by 2012 minus 2009, so it'd be 3. So when I do that quotient of 3.68 minus 2.41 and divided by 3, I get 0.4233. Okay, so, and that's in dollars again, so 0.4233 repeating dollars. Okay, and you see then that when I choose these different years, essentially different sets of ordered pairs, that number there, the average rate of change between 2005 and 2009, is different than the average rate of change from 2009 to 2012, which is going to be different than the average rate of change from 2006 to 2010. If I go 2006 to 2010, what is it? 2.84 would be 2010, and then 2.62, and then we're going to go, so what is that? 4 years. So then I have what, 0.22 divided by 4. Evaluate that, but that's going to be different than these two. So what happens is it tells me that based on what we know about this thing here, and we said if f of x equals ax plus b, then the average rate of change is slope, and we went through and said, well, that means it's constant. And it's really a biconditional. If your function is linear, then the slope is constant, the average rate of change is constant. And if the average rate of change is constant, then your function is linear. So it's an if and only if statement, essentially. So when they ask you, is this function linear or nonlinear? My answer is it's nonlinear, because the average rate of change is not constant. Okay? Here's another situation. And this might prove to us that when the average rate of change is not constant, that the function is nonlinear. We automatically know this is nonlinear. Okay, nonlinear, not a line. And it asks me to find the average rate of change on the interval of -1 to 2. So what that means is, and this is an instance, guys, where we need to know what interval notation means to us. So I go -1 to 2. So x is -1, and I'm going to go to x being 2. Okay, so it says average rate of change on the interval. That's telling me what x values I'm going to look at. Okay, so when I find the average rate of change, I'm actually trying to figure out what is the slope of that dotted line. And what it means then is, so this point here is -1,4. This point here is 2,1. If I do change in y over change in x, okay, so now I want to make sure that I understand that I'm going left to right here, so my slope is going to be decreasing, okay, so I'm going to go 1 minus 4 over 2 minus -1. That gives me -3 over 3, so it gives me -1. And what that means is that as long as I apply, if I go from here and I decrease my amount by 1 for every one interval or one unit on the x-axis, so essentially go down 1 as I move over 1, down 1 as I move over 1, down 1 as I move over 1, it's going to get me from that point there to that point there. So now here's the question is, well, what does this look like when I go from, let's say, this point here? So I'm going to go on the interval 0 to, let's go 3. So in that case, I'd be looking at the ordered pair 0, 1. 0, 1's that order pair, and then over here it'd be 3, 4. So now when I do delta y over delta x, you see that I'm increasing, so it'd be 4 minus 1 over 3 minus 0, so that gives me 3 over 3, which is 1. And you see that those two average rates of change are different, so that's consistent with it not being a linear function. This is non-linear. Up 1 over 1, up 1 over 1, up 1 over 1 gets me right there. So along that duration, this interval was 3 units long, and my change in the vertical distance was 3. So that's where I get this 1. Alright, so this one talks about the average rate of change of a force. It says the electrostatic force, capital F, measured in newtons between two charged particles, can be related to the distance between the particles d in centimeters by the formula F of d equals 2 divided by d squared. It says find the average rate of change of force if the distance between the particles is increased from 2 centimeters to 6 centimeters. Alright, so all I've got to do, this is the idea, is we're going to find F of d2 minus F of d1 divided by d2 minus d1. And all that is, it's the same as F of x sub 2 minus F of x sub 1 over x sub 2 minus x sub 1, or y2 minus y1 over x2 minus x1. Okay, it's my output difference divided by my input difference. So I've got to evaluate. I got to figure out what those are here. So we'll have d2. I'm going to use that formula there. So I'll just erase the other two. So we're going to have F of, so d2, so here's d1 and here's d2. So we'll have F of 6 minus F of 2 divided by 6 minus 2. So F of 6 would be 2/36 minus F of 2, which would be 2/4 all over 4. Okay, so this is, I need common denominator, so it would be 9. So what, 2 minus 2 minus 18 over 36 divided by 4. So it gives me negative 16, 36 times, so this is over divided by 4 over 1, so I'm going to change that to multiplied by 1 over 4. Those cancel, leaves me 4. So then I get negative, 1/9. Okay, so negative 1/9. Okay, and that should make sense if we understand what electrostatic force means. That electrostatic force should decrease as my particles, the charge is stronger when my particles are closer, and when they get further apart, it gets weaker. So that's what this negative is showing me. Find the average rate of change here of f of x equals x squared plus 2x minus 8 on the interval of 5 to a in simplest forms. Okay, or in simplest form, I cut off here in terms of a. Okay, so this is the same idea. I just don't know. Here's my inputs. Okay, and I want to figure out what are my outputs. Okay, so the first thing I have to do is figure out, so if I'm on the interval from 5 to a, so graph, so x squared plus 2x minus 8, I don't know exactly. I know the y-intercept is going to be negative 8. My graph probably looks maybe something like that. I'm not sure. Okay, it might be over to this side instead, but regardless of that, 5 to a, so would mean 5, and then maybe A is somewhere over here. Okay, so it's showing me that relationship. So I'm going to try to figure out, okay, well, there's going to be a point up here on the graph and a point down here on the graph, and we're trying to find the rate of the change between those 2 points. So when I'm trying to evaluate this thing, okay, this is essentially my x1, and this is my x2. So I'm going to find f of A minus f of 5, and I'm going to divide that then by A minus 5. So f of A, all that means is come to the function f and plug in A everywhere you see x. So I'd have a squared plus 2a minus 8. Okay. Then we're going to subtract from that. F of 5. Well, f of 5 would be 25 plus 10, so there's 35, minus 8, which would be 27. We'll divide that then by a minus 5. So we get a squared plus 2a minus 35 all over a minus 5. And what's nice about that now is that that is now a rule that's going to allow my average rate of change to change from, so if I'm working on this parabola, so what is this? This factors to, what, x minus 4 plus 4, x minus 2. So 1, 2, 3, 4, 1, 2. So my negative 8 there. So my graph would actually be something like this. Okay. So if I've got like 5, and then let me do it this way, just to make things a little bit easier to draw. Let's not force me to know what my scale is on the bottom here. So I'm gonna make this a little bit shallower. So let's say that's my parabola. What this allows me to do is say, okay, well, if that's 5 and that's A, I can figure out what that average rate of change is now using this formula just by plugging in A. So let's say A is 6. Well, if I plug 6 in now, I automatically know what the average rate of change is between those 2 points when A is 6. And if I say, okay, well, what if A is 7? Just plug 7 right in here. It tells me the average rate of change between 5 and 7. Instead of having to go, okay, well, if I want, let's say I have a series of these, I want to find the average rate of change between 5 and 6, 5 and 7, 5 and 8, 5 and 9. Well, if I don't have this, then basically what I need to do is that entire process that I just did with 5 and 6 as my inputs. So I need to evaluate this thing at 5, evaluate at 6, subtract them, find their difference. The difference between 5 and 6, and then divide. Then I would need to do the same thing with 5 and 7. Evaluate this at 5, evaluate at 7, subtract 5 and 7 on the bottom, so divide by 2 eventually. And so I'm redoing the same exact procedure over and over again for each iteration, where if I just make this second point arbitrary, make A arbitrary, I can get this rule, and then it makes the process of finding the average rate of change between 5 and 6, 5 and 7, 5 and 8, 5 and 9 so much more efficient. I can actually make a function now that would even produce those results quicker. Something that we get into in calculus. So I kind of alluded to this the other day. I just want to double check, make sure I get some time here. All right, we're good. Was the idea that we're going to want to be able to find like maximums and minimums, and ultimately one of the key things in calculus is finding slope of a curve at any point. So I might want to know, what is the slope of the curve here at f, and how does that differ then from the slope of the curve here at g, and then how does that differ from the slope at g there or g there. So the way we talk about that or analyze that is actually through the use of a formula very similar to this. Okay, all this is is a restructuring of what I just talked about. Okay, what we have here is we have f of a plus h minus f of a. Well, a is an input, so a is an input. Okay, which means it's a independent value, so it must be representative of an x value. A plus h is another input value, okay? And all that means, so if I have a and then I have a plus h, well, if a was like 3, then a plus h would be 3 plus something, so it's going to move it to the right. So a plus h is going to be to the right of a, graphically here. Think about what h is, okay? Think about what h is. That is that distance right there, okay? So when I ask f of a, so I'm going to have a point right here, and I'll have a point maybe right there. Oh, right there. Now, I might have in between these 2 points, my graph might do something completely bizarre or unknown to me. But if I want to find the average rate of change from that point there to that point there, it is the slope of that line. Well, think about what we're doing here. What's f of a plus h? It's a y value. What's f of a? It's another y value. And if I think about h here, that was this distance. Well, isn't that an x2 minus an x1? Isn't that how, if x2 is a plus h and x1 is a, subtract those, don't I get h? So you're going to see this formula, okay, a lot when you start working inside calculus. It is simply a slope formula, okay? It's changing y's divided by changing x's, okay? But let's kind of talk about what this does for us. If I look at this here, okay, as I move these points, what it's going to allow me to do here is determine the slope of, or the average rate of change of the secant line, or secant segment, sometimes called the chord, depending on how much of the line we actually look at, between those 2 points F and G. Okay, so all I've got here, you can see as I move F, okay, it's moving this A, which is the X coordinate of F, and it's moving this Y, which is F of A, okay, which is the Y coordinate of F. And same thing for G, okay. So if I show you what we call our secant line, okay, or if I show you just the chord, okay, if I show you the chord, what we're trying to do here with trying to figure out the average rate of change from F to G, the average rate of change from F to G is that distance, which is the vertical distance between F and G, divided by this distance, which is the horizontal distance between F and G, and that's the average rate of change. Now, how does that help us in calculus? Well, in calculus, we like to look a little bit more than just the chord. We look at the secant. And what we do in calculus is, if I'm trying to find the slope, but let's say, I'm just going to put an extra point in here. Let's say I want to find the slope at point P. Well, what we do then is that we take this point F and we take this point G and we try to get them infinitesimally small. Okay? So what that does, if I can get them infinitesimally small, the distance between F and G to be so small that we get our secant line to actually become a tangent line, okay? And then the slope of that tangent line is what the slope is of the curve at that point P. If you watched what happened here, what happened to A and H? A and H, there's still a distance between them because my 2 points F and G were not on top of each other yet, But what we want to do is we want to make sure that number goes to 0. Now, it can't go to 0. It can't become 0. Because think about what happens. So that distance h, if it was 0, we'd have problems here. We'd have division by 0. But what we want is that we want the idea that it becomes extremely close to 0. And we talk about limits. And we'll talk about limits towards the end of the year. And it'll be, when you get into calculus, it'll be like the first month and a half that you talk about them. But in getting to that point of being able to say, okay, well, what is the slope of this function? Okay, what is the slope? Let me go back to standard view. What is the slope of this function at point P? It's the slope of that line right there. Okay. I don't think the ability to actually ask GeoGebra to say, if I type in slope, yeah, just ask for the slope of a line. I can't tell it the. Sorry. I think if there's a way I can show you that this is the slope here. Let's see here. The slope of this line here is 0.53. If I look at the average rate of change between F and G, then, okay, would also be 0.53. And the closer F and G get closer to one another, now it's not letting me pull those points any closer, that 0.53 will become a better approximation for the slope of that point on that curve. If we knew a little bit more calculus, I could show you some numerical relationships that would make things maybe seem a little bit more concrete to you. But what I'm trying to at least open your eyes to is that what we're about to do here is going to be something that you need to be able to do once you get to calculus. Okay, so I'm going to go through that preliminary work with you right now. They're going to give you in your homework this function, or this rule. Okay, it's average rate of change rule. And when we get into calculus, we'll call this the derivative. Here's the function that we're interested in doing this on. Okay, so what we're going to do is we're going to say, okay, if this is my function f of x, let's figure out what f of a plus h looks like. So all that means is that now becomes your x. So you're going to rewrite this as f of x equals x squared, but now instead of x being the input, a plus h is the input. So now you're going to have a plus h squared minus then f of a. Well, a is now your input into this function. So now it would be a squared. And now on the bottom, okay, we just have h. Sometimes in early on in like a calculus class, you might see that it's written as a plus h minus a. That's your x2 minus your x1, but the a's cancel out, lose just that h. But now it's going to ask you in your homework, can you simplify this? Well, this is going to give me a plus h squared is a squared plus 2 ah's plus h squared minus a squared all over h. Okay, so I just expand that, okay, FOIL it out, and you see here that you got a squareds, and they cancel out. One's positive, one's negative. So now I have what we call 2ah plus h squared over h. Now all of these have an h in them, so we'll cancel that, and I have 2a plus h left over. Okay, now that'll be what your answer is in your homework in this section. But in calculus, what we want to do is say, okay, well, what happens when that number, because remember what h is doing when we're trying to estimate this slope. We're trying to estimate the slope. H, remember, was the distance. H was the distance between these 2 points here, and we wanted that distance to become infinitesimally small. We wanted to get to 0. So let's make the assumption that if it becomes 0, all we're left with is 2a. Okay, so here's my question. And this is maybe where we can make a recognition about what's really going on here. We get the slope of 0.53. I'm going to look at this point of A right now, this point of A, which is located, see if I can get its coordinates, object properties, name and value. That's not going to work. It's not going to work based off the way I've got this set up. It's not going to show you the relationship. But basically what what goes on here is this becomes essentially a rule for finding the slope of anywhere on my graph. Okay, now it's not necessarily working because of I'm going to show you all the constructions I've got going on here just to prove the point that I was trying to get initially. There's a lot of stuff going on here that are isn't allowing me to show that slope. But what this allows me to do is say, okay, well, A now is going to be some x value. When I plug that x value in, let's say x is like this point, like right here, plug that x value in, it's going to give me what the slope would be right there for that blue curve. And I come over here and say, okay, well, what if I want to use this x value? What it would do is it would give me the slope of this curve, or the slope of that tangent line, essentially, at that x value. So this ends up being, when we get to calculus, that ends up being what we call the derivative, okay, which is essentially a rule that allows you to find the slope quickly by just changing the input or the x value of where you want to find the slope. And I know that might be kind of confusing to talk about because of our lack of knowledge right now about calculus. But again, my purpose of discussing this is, one, I've got a couple questions in your homework that ask you to do this. It's just evaluating functions at a plus h and a, doing some algebra with them. But two, after we get through this course, you'll have a greater understanding of that preliminary calculus stuff, that algebra, and then when we get to calculus next year or whenever you take it, like I said, that first month and a half is all about using this formula, using derivatives and limits, or limits to find derivatives. One thing that people struggle with in calculus is that we use this idea of trying to get things infinitesimally small, but not necessarily zero, but small enough that we can assume that it's zero. Your homework shouldn't be, I think it's like 8 questions, shouldn't be overly taxing. But average rate of change, what I need you to understand, for a line, it's constant. For nonlinear functions, it changes depending on where you're located and what order pairs you're looking at.